So we saw, we saw the security block, we saw the data processing block, the CRC block and all that. So event link, I'm not going into too much detail. It is something to do with how you want to link some different interrupt events and handle things together. I'm not going too much into details of that. Then the next important block is this analog block. Right? So we'll look at what are there in the analog blocks. Okay. So why do we need an analog block? First of all, we said embedded systems typically interact with the environment, they control external things. Okay. So why do we need an analog block? First of all, we said embedded systems typically interact with the environment, they control external things, maybe a sensor or they read a sensor or they turn on a motor, they probably have to drive some power electronics. They have to do, and many of these sensors will typically give you some analog inputs, right? Typical sensors, for example, if you take maybe a thermal sensor, right? There may be two pins from the sensor. One you connect to the ground, one you connect to some analog input. That output on that pin may be a function of the temperature. Either it may go up with temperature, the voltage may go up with temperature or go down, depends on the device. But there's a relationship with the temperature and the voltage on that pin. Now, that sensor is just a simple device which gives an analog voltage. Now, I want to be able to check the temperature and take some action, right? So how do I do that? So I need a device which can, because our computer is a digital computer, right? We talked about digital computers. All the processing I can do only in the digital domain. So that analog value, if it's say 8 volts, I have to get it in binary form as 1000. Then I know it's 8 volts and I can process it. I can compare it, whether it is high, low, and take some action. Suppose the voltage has gone beyond that. Suppose that's a software managing the temperature, thermostat control on a AC, right? When the temperature goes beyond 28, I want to turn on the compressor again. So basically there's a pin which there's a connected to a thermal sensor. That pin is giving a voltage. Now that voltage may be having some different levels. Maybe like 5 volts means 20, 6 volts means 24, 7 means 28 and so on, right? Now I need to be able to measure the voltage and take action. But my software is running in the digital world. I am processing, I can only deal with numbers which are in digital format. So this voltage 7 volts, which is an analog voltage, I can measure with a voltmeter. It may show 7 volts, but it has to be converted and I should be able to read it in the program and manage. So that is where an A to D converter is coming into place. So what is the job of an A to D converter? A to D converter, one side if you give this 7 volt, say a voltage level, it will give you a resistor on the other side which you can read, and that resistor will have a binary value of the voltage, right? If this is say 7, you can read binary 7 there. If it is 8, you can read something like that, or some ratio of that, right? So essentially an A to D converter helps to convert an analog quantity into a digital value which you can process. So is that clear why we need it in digital world? Similarly, the other way is digital to analog. Suppose I want to control the speed of a motor. I mean, let's take a very simple case. Assume the speed of my motor is dependent on the voltage I put out. It may not typically be always the case, but simplicity's sake I'm saying. So, or the intensity of a bulb, right? I want to have the intensity of the bulb directly say proportional to the voltage that I give. Now, I can generate all the voltages from say 0 to 10 volts. I can generate the numbers in my program as 0 to 10 in binary value, but that has to be finally given to the bulb as a voltage. So this is where a D to A will come. So my program will go and write the value 5 to a register. The DAC, which is called the digital analog converter, will take that value 5 and it will have one pin output, which is an analog output. There you will now see, if you put a voltmeter and measure there, you will see 5 volts there. If I write 7 to this, immediately the voltage there will change to 7. So that is called as a digital to analog converter. So if I want to control things, external things, typically I will need a digital to analog. Controlling things will need a digital to analog because I'll have to either drive a motor or a bulb, or it could be anything, right? Or there will be other things which I want to control, which are all driven by a digital value which gets translated into an analog voltage of some kind, which in turn may trigger some action. That voltage may trigger an action which is like intensity of the bulb or a speed of the motor or anything else for that matter, right? So all that is possible. Whatever you want to do with it is up to us, or you want to change something, move something, all are possible with that. And similarly, lot of sensors. I mean, I just talked about thermal sensor, but there are so many sensors. Most of them will give the value as an analog value of some kind, maybe positive, proximity sensor, ultrasound, devices. There are so many sensors available today, but to interface them to the microcontroller based system, you need the A to D block. So if I'm building a pure electronics, I can completely build with analog electronics. I may not need a sensor conversion, but typically if you're coming to the microprocessor or microcontroller based embedded system design, then you will need a converter in between to convert from the analog world to the digital world, process and send back the output. The action again happens in the analog world actually, okay. So these are things which are there, and there are, I think the support it has got a 14-bit analog to digital, which means any analog value is converted to a 14-bit value, which means that is the precision you can get. You can probably there will be different programmable controls for that block, but you can get a range of values. Maybe for example, 2 power 14 is how many values? Like it is 16,000, I don't know. 2 power 16 is 65, 536, like 32, 16,000 values approximately, right? So if you have a voltage range, you can finally divide it into that many, the precision you get is so much. Say 0 to 10 volts gets translated into, say, a 14-bit quantity. So that is the precision you can expect, right? 0 may be 0, 10 volts may be all 1, 1, 1, 1, 14 bits of 1. Anything in between, you can find out the precision that you need actually, okay? Which means you may be able to measure things like 1.234 volts or whatever, right? You have to calculate and see what is the precision you get, but that's the more the number of bits, you get more precision actually, okay? Similarly, there's a D2A, which is you write a 12-bit value, it converts to analog. There are two types. One is with an output amplifier, which means it can drive probably a larger current. See, when you want to drive an external electronics, right, your current output should be more. Maybe the microprocessor itself sometimes cannot supply so much of current. So this, I think, has an inbuilt output amplifier, which is probably an analog block, which can drive more current. It's part of the chip itself. And there is another DAC without an output amplifier. I think this is used to generate some reference voltages for some other functionality. Things like another interesting chip device on this called low power analog comparator. So for this comparator also, this DAC is used. Suppose I want to kind of compare external value, right? It's an analog comparator. So what I can do is, instead of converting to digital and comparing, so the way this works is this 8-bit DAC is used to generate some value. So I can generate a 5 volt by programming this 8-bit DAC to something. And then I can configure this low power analog comparator to compare with this 5 volts, and I'll get a signal saying whether it's high or low. So why it's called low power is comparing the analog domain is less power consumption actually. So this is a device peripheral which is available here. It has also got an inbuilt temperature sensor. I think it's an on-chip temperature sensor. Then there are some operational amplifiers for simple op-amp type of functionalities. So these are all the hardware, analog blocks which are there in this device, which is quite an important thing from an embedded system perspective, because you need a lot of these analog interfaces, right? To build any typical embedded system, you will need those analog interfaces to measure, sensor, or to control things. So this is something which is quite useful for embedded system perspective. So I think we have kind of pretty much covered all the blocks on this Renesas processor. We saw pretty much all the functionality. Now we'll move on to a final couple of slides on typical embedded system software, right? I think so far what we have seen a typical embedded microcontroller. We took the Renesas chip as an example, and we saw all the different blocks and peripherals on the chip and what is the typical functionality and why we need them. We just got an idea about it. Now we are moving on to different ways of building the embedded software, okay? The simplest form of an embedded system is built like an endless loop, okay? So if you take the software and see, all you will see is one big infinite loop, typically while one, and a series of things will be happening. So basically the code will go through a series of checks. Maybe it'll check something, do something, check something, do something, then go back and start the whole process again and again. There are a lot of simple embedded systems where this is a good enough architecture, where if the job is something very simple, this kind of an architecture is good enough, and you can control, the exact sequence in which things are happening. I'm going to check this first, next this, next this, next this, then take these actions. Maybe wait for some time, maybe I may sleep, I may not do something, I'll probably set a timer, sleep for some time. Once the timer goes off, then go back and do the same thing again. A lot of embedded systems work in this fashion, okay? So simple embedded systems, this can be done. So it's entirely in the control of the designer. You design the loop the way you want, and you know all the constraints of your system. You do the entire design yourselves. Then the next step, where you want a little more complexity, where you want to partition the functionality into different tasks or whatever, right? You build your own simple kernel. A kernel gives you basic functionality like what? I want to have a task abstraction. I should be able to create tasks. A task is nothing but an independent control, basically a flow of control. So I start a task, I will say this, I'll give a function as an entry point, and it starts running from there. So that control keeps going from there. Whatever function that in turn calls, it will keep running. Similarly, I can create multiple tasks, and then I may need to have some simple ways to communicate between the tasks. The simplest form, maybe I'll just use some shared memory. All the tasks have access to the common memory. I may define saying task A to task B, I will store something here. Task B will read from there. Other way, task B writes here, I read from there. There may very, very simple mechanisms you can set up, and you can still design a system. So your system is a little more complex than a right loop kind of an architecture. You can go for a custom built kernel, but it's a little more work where you have to design the kernel properly. You'll have to build your own scheduler, communication mechanisms and all that. Typically, companies do it if they have a long history of doing things, right? You develop a lot of products and you have a good team which has invested time in building this kernel. They keep reusing it. Building one for just one project is probably not feasible, because it will take a lot of time to design that kernel in a proper fashion with all the primitives properly built in. It may not be easy to build it properly just for one product I'm building. Typically, this will be done by a company which is having a series of products, right? So then you invest one team may be just building this kernel and giving it to all the product teams. They'll all be using this and building products based on the kernel. So this team may be continuously improving this kernel in terms of functionality and all that. That's why if you look at companies like Cisco or many of those big companies, right? They started building their own kernels. Cisco has a own kernel called IOS. They call it Internet Operating System or something. That's their own homegrown real-time kernel. They use it for most of the products. I don't know, till a few years back, they were still using it in many of their mainstream products. Many other companies may be having it. Companies which build their own simple embedded devices may have their own kernels to use. Other step would be to grow to probably a commercial real-time operating system. There are some free real-time operating systems also which are good, like there's something called FreeRTOS, which is a real-time operating system. May not be as complicated as things like VxWorks or QNX, which are popular commercial grade RTOSs. The good thing about them is they come with a lot of support. They'll have extensive mechanisms for task creation, management, very good scheduling classes, different priorities, priority-based scheduling. They'll have a lot of support for multiple communication, like inter-task communication, synchronization. They'll have excellent primitives for all that, and they will also support a lot of libraries for things like networking and so on. So, but they still give you a lot of real-time guarantees. If you want to build a hard real-time system, right, you'll have to use one of those good quality RTOSs. If you want to build a hard real-time system like what I talked about, like a rocket system or something, you may need a good quality real-time OS which guarantees, because the scheduling algorithms they use, you can design with the right priorities. You can make sure that your highest priority tasks really get that attention immediately when an event happens and so on. So this is a class of systems which use commercial real-time operating systems. Typically these will be hard real-time systems. Then the final one, which is quite popular for a large class of systems, is Linux. Okay, Linux started out as a general purpose operating system. We have Linux desktops which people use, but what people found out is because it was free, so there was a lot of motivation for many companies to see whether that can be used for my embedded device. So this trend started even way back in Linux became popular on the desktop, or just started coming out in the mid 90s, or I think early 90s to mid 90s. Slowly people started hearing about Linux, right? But even by 98, 99, a lot of companies figured out that the kernel is good. It was already supporting a lot of networking peripherals and all that stuff. So many companies started trying to use it as an operating system for an embedded device. Especially the trend started mostly with, say, communication devices, networking devices, routers, switches. Many of them started using Linux because it was good enough for their needs. And Linux also started supporting some different scheduling classes. You could actually change the scheduler to give higher priority to some of your tasks. They brought in things like real-time scheduling classes and all that. Using some of those extra support that became available, people were able to build good quality embedded systems with Linux itself. It may not support hard real-time, like the critical things that we talked about, but a large class of systems like routers, switches, home modems, many of them today use Linux actually. So because one of the biggest advantages of Linux is one is it's free and it's open source, so a lot of people are working on it and it's well supported, and it now has got a support for a huge amount of peripherals, protocols, file systems. So pretty much everything that you want for a device. If you want to connect to the internet, all the TCP/IP stack, a good quality stack is available. I want to connect probably a USB drive to my embedded device, that support is available. USB support is available, file system support is available. Pretty much everything that is really needed to build an embedded system for many devices, it's available on a Linux platform. So that's one of the reasons Linux has become very, very popular in the embedded world for a large class of devices. Wherever you can afford, see, only problem with Linux is you need a processor which probably supports an MMU, which means it's not the Cortex M series type of processor, Cortex A or something like that. And typically the applications also need that kind of processing power. These will be processors which can run at multi hundreds of megahertz or gigahertz or whatever. Because if I'm building a router, I need that kind of processing power to process the packets that come in at that speed. So those devices typically have a full-fledged MMU. So I can run a proper Linux on that device and then build all my application on top of it. The set of system calls that Linux supports also allows you to build a complex system very easily. And and today a lot more middleware components, right? There are a lot of open source middleware components for things like databases, key value stores, and many things are there. Today modern systems use many of that, and support for different programming languages. So it's easy to do development on Linux and build a complete application in a very robust fashion. And that's one reason why Linux has become quite popular. So it is good, as I said, for soft real-time kind of functionality. It may not be good for hard real-time applications, but soft real-time, a large class of devices fall into that category. So it's good enough for that, and that's why most of them use Linux today for embedded system development, especially this class of device. Today, for example, you talk about Android TV, right? But again, basically Linux and the Android layer on top. Mobile phones run Linux. Basically, Android is nothing but Linux in some form. So that way, Linux has become extremely popular for a lot of many home devices. Home networking devices use Linux. So you don't see it generally because, so if you have a home router, they don't allow you to directly log into that Linux as like a regular user, right? That's all blocked. You can only connect with a browser and you will see one user interface. But underneath that, Linux is running. Because again, the same reason, right? They don't want you to allow you to run arbitrary program. Because it's Linux, if they allow you, you can download something and run it there. but they don't want you to do that because it may mess up with the system's performance and all that. So only thing they allow you is to connect with the browser. You'll see a user interface. If you are configured your home modem, right, you'll connect to 192.168.1.1 or whatever. You'll see your interface. Admin login they will give you, but you will only be able to do minimal things, right? Maybe configure some DHCP, configure parameters or whatever, and then it will go back to it. So they don't allow you full access, but underlying pretty much it's probably running Linux actually. So that way Linux has become quite popular in the embedded world for a lot of these applications, and it's continuing to grow in popularity because a large set of systems can be successfully built with Linux. So you can see here, right, Linux itself, so many flavors of Linux are there. See, in all these things, one thing I have to remember is the Linux kernel is the same. So all the names that you see here, like Ubuntu, whatever, right, Debian and all that, these are all the things that they build along with it and ship it. So what is called as distribution, right? Along with the core Linux kernel, they add their own set of libraries or set of things that they choose to package and distribute, their own package manager. So those are the things which are different from each one of these things. But pretty much all of them underneath what is there is basic Linux actually. But there are many versions, you will see CentOS, Ubuntu, Xubuntu, there are a huge number, the Red Hat, but pretty much the kernel you have to understand is exactly the same. So the kernel, the system calls, everything is the same. Only what ships in the distribution is different. If you install Red Hat Linux, you may get certain things as standard. If you install Ubuntu, you may get the UI which Ubuntu uses may be different from what Red Hat distributes. So those are all the differences. But underlying kernel, it's the same standard Linux kernel. Whatever version of Linux kernel they're using, it's the same actually. So just to illustrate one example, right, that endless loop I talked about, right? We talked about that underground sump, water pump example, right? So that embedded system can be very simple. It will just say while true, which means it's like an endless loop. Like it will keep, once it enters this loop, it keeps running this loop. What can it do? We can write code to first check a water level sensor in the overhead tank, right? We get a value. All this you have to imagine what all happens, right? What will happen? When I read the sensor, ultimately the sensor is connected to some A to D and I get a digital value. So the program actually reads the digital value, right? Okay, that's what the program can process, right? The sensor is connected to one pin and it converts to digital. That is available in some register. When I say check water level sensor, I'm actually going and reading that register, I get a value. Now that may be a number which I can compare. Now there may be a threshold set. Overhead tank level is less than the threshold. The number which I'm reading is below a threshold, which means there is space in the tank to pump water above. But now before pumping water, assume I'm pumping water from the underground sump. Now I have to check underground sump has water. So I check one more sensor which gives me the reading of the water level in the underground sump. And assume I don't want to put the motor which is very low, then the motor may get airlocked or whatever. So I have some lower threshold. So the sump water level should be greater than that threshold. So what is this condition is? First I check whether overhead tank level is less than threshold, which means I can pump. Then I check whether there is water to pump in underground. So if there is enough water to pump, then I say turn on the motor to pump water to the overhead tank. So this is, if you look at this action, right? Here you will be typically using your DAC. I am writing some value to the digital analog where, or maybe I may writing to a GPIO pin, it depends, right? Or I may be triggering some relay. The relay may be connected to a GPIO pin is nothing but a pin which may have a 0 or 5 volts, right? It may be connected in turn with by a transistor to a relay. So if I write a 1, the relay may be switched on. If I write a 0, the relay will be switched off. So it could even be a relay, depends on what type of system we have designed. So I turn on the motor, right? Now the motor starts working, water is going up. Now what I have to do, I'll have to make sure that the overhead tank is not, the moment the overhead tank gets filled up, I have to switch off the motor, or the water in the underground sump goes below a lower threshold, I should stop. Otherwise there'll be airlock. So what I do, then I enter one more infinite loop here. Infinite loop in the sense till some point. Then I keep checking. I'll turn off the motor and I break underground sump. Then if either infinite loop here, infinite loop in the sense till some point. Then I keep checking. I check the overhead tank and I check the underground sump. Then if either overhead tank is full or the underground sump level water is coming below a threshold, I'll turn off the motor and I break. A break means I'll come out of this while loop. It'll come out of the innermost while loop. This break will come out. Once I come out, I'll come here. Then what do? I go and sleep for 1 minute. Basically, I'll program a timer. I'll then go into a sleep state, which means I'll not do anything. I'll be waiting for the timer to trigger. Because I have decided, what does this mean? I'll be checking the levels of my overhead sump every 1 minute. So if the sump becomes empty, overhead tank becomes empty, up to 1 minute, it may take for me to turn on the motor, right? If I want more faster response, I will make it say 10 seconds or 5 seconds or whatever. Lower than that doesn't make sense, because unnecessary check. So here I have taken my decision as 1 minute, I check that. And here, in this case, this inner loop, how do I check? Here motor is actively running, right? So here, I only sleep for 1 second. So as long as the motor is running in this while true, this inner loop here, can you see this loop? Here what I do, I check the overhead tank and underground sump. If I need turn off, I turn off. Otherwise, I just leave for 1 second, go back and check. Which means maximum water will overflow for a second, which is tolerable, right? So that's how you design the timing constraints or depends on the application, right? So here, so these are all the places where you'll use your timers. So the timer blocks that you have, right? You can use one timer for this, you can use one timer for this, so that your system can be easily designed. You don't need anything else. So this is all you will have to be. So this is a very simple piece of code, right? This may hardly be some, I don't know how many lines of assembly, 200, 500 lines of assembly. You have to just check some sensors, trigger some relays, sleep. For sleeping also, you're using the timer devices, and sleep may technically be in an endless loop, not doing anything, be like a null loop. You're just waiting for something to happen. When it happens, you jump and take that action actually. So is this clear? An example of how an endless loop is designed, okay? So if you talk about an RTOS, RTOS supports these things, right? Things like a task abstraction. As I said, task is nothing but a sequence of, a flow of control, okay? So to understand this concept, right, what is a flow of control? See, we already saw how a microprocessor operates, right? So what does a microprocessor do? Microprocessor keeps fetching instructions in sequence. As long as I don't stop it, it keeps fetching instructions in sequence and keeps executing, right? Assume, I have one function, say, let's call one function f1 in C, and I have some code here, okay? Assume this is again, assume for simplicity, this is like I'm just trying to simplify this task concept for you. So assume this is a infinite loop, which is checking some things and continuously doing it, maybe sleeping in between. There is one more function, say f2, which also has a very similar structure, okay? So this also has a loop, infinite loop. It does certain other things, it does something else, maybe it's checking some other sensors, right? Now, in my system, I have what is called as a scheduler, okay? And I have only one CPU in my system, one CPU, right? Okay, so imagine what is this f1? Ultimately, when the C program gets converted, it is a series of assembly instructions, okay? So f2 is another series of assembly instructions, right? Getting it? So this may be some, say, address X, this is address X and this is address Y. So maybe each of these say 100 instructions, right? Now, what do we know when the process starts executing here? This instruction, next instruction keeps going like this, right? Assume, how does a scheduler typically run? Scheduler are generally done by using some interrupt mechanism. I said the interrupt is something which interrupts the flow of things. So assume there's an interrupt which comes every 10 milliseconds. So assume this was running, 10 milliseconds expired and an interrupt came. So when the interrupt comes, I'll make the scheduler code run, okay? The scheduler is nothing but a small piece of software. Typically, it's written in assembly. What it will do is, when it enters the scheduler, see, this process was running, right? So any CPU, what are the resources inside a CPU? You have registers, right? You have a stack pointer. So you typically, these are all the part of what a CPU runs, right? And there's something called as a program counter. A program counter is a register which tells the next CPU instruction, next address where the instruction has to be fetched, right? So for this task, you can say this is what is called a context of a task, which means the CPU only depends on these things when this particular function is running, right? All the variables, everything is probably in some registers. Maybe it has some associated memory. Memory is anyway independently assigned to that. But other than that, it may have some temporary values in the registers because assembly program may be using some registers. And it is about to execute the next instruction. The program counter is pointing to the next instruction to be executed. At that time, an interrupt comes, the scheduling interrupt comes. See, normally when you jump into the scheduler code, as soon as I come into the scheduler code, what I will do is I will save all these registers into some space, okay, some part of memory or some area. I will save all this data, right? Okay. Once I have saved this, I am now free because all the information about this process is part of this. The value of the registers, what is the next instruction it is about to execute, the stack pointer value, all that I have saved. Now the scheduler can actually switch to another task. So you can imagine initially this task also has got all this value stored, or maybe I'm just going to start this task. It has no context. So what I will do is when the scheduler comes, I will say, now I have given you enough time to run. Now I'm going to let F2 run. What it will do is it will go and change the program counter value to be the start address of this, which is Y. And it will kind of exit from the interrupt service routine. When it exits, it will automatically, because the program counter value, it has modified appropriately. I'm not going to full details. Logically, you can assume this will now start running. Okay, because the program counter is now pointing here, it will start running here. And suppose another interrupt comes here, another scheduling interrupt comes here. Now it will come here, it will say, okay, Y has run for enough time. Now, whatever it has saved, right, all these values. So that scheduler will now copy the saved values into all the registers, stack pointer, and it will know when it returns, the program counter will point to where it should have been executing before it took the interrupt. Okay, so this is what is called as a context of a a task or a process. So all you need to be able to stop something and continue execution is to save all the registers, stack pointer, what was the next instruction that sequence is going to be executed. So you give it back and let it continue. Now it will appear that this task is running. So both these tasks, for simplicity, we have taken just one function each. So what will happen is when this interrupt keeps coming, you will see this code running, this code running. So this is called as a task scheduling, right? So a task is nothing but a sequence, a flow of control. Because the moment I call a function and give it control, right, it's going to continue running whatever code is there in the function will execute. If that function calls another function, it will go there, execute that, keep coming back here. Or if it's a simple case like this, it's a while loop, it's forever going to be running in that function. So we can, for simplicity, we can look at this as one task, this is another task, and you can switch between the tasks using a scheduler. A simple scheduler which is able to save the registers and restore the registers is able to achieve what is called as a scheduling. This is called as, task scheduling or whatever. So in a real-time operating system, the memory is common. All the tasks can access all of the memory in general. So it's kind of a shared memory architecture. So there's not much of protection between each other. The simplest operating systems, real-time operating systems don't give you those things. And they will have some ways of communicating. So we talked about scheduling. So this is called as a task abstraction, basically a flow of control, how something can run and how you can switch between them. Then inter-task communication. So I have completed something, I want to indicate to the other task, now you can do something else, right? For example, I have initialized something, now the other task has to probably write some values there. So I can send there are messages, there are things like message queues, shared memory, different mechanisms by which the task can communicate with each other. Then there are something called synchronization primitives. For example, I am accessing a device, and assume the device is something like where only I have to program a series of things. If somebody comes in between and tries to write to the same device, it will get messed up, right? I may have to write a sequence of bytes. So if I am a task, I want complete control of the device till I finish my sequence, right? So these are called mutually exclusive things where only one task can do it. So here you will have things like, again, some support things like mutex locks, semaphores, and so on, which the task, because the entire thing is written by you, so you design it in such a way that they will all first acquire a lock or a semaphore, then access that device and release it. Then the next one will be able to get access. As long as this is locked, the other task, even if it tries to access it, it will be put in a wait state. These are all the functions which the RTOS gives you. I mean, you don't have to worry about how it is implemented. I was just giving an example, but ideally, these are all primitives which are available by in an RTOS. So if you are designing a system, you will have to use these primitives to make sure that critical devices are accessed, in sequence, and you are not overlapping with each other and so on. And RTOS will also give you a good amount of device driver software. All the peripherals will be well supported, networking support, protocol support, all that will be there. And so as I said, if you're building a custom build kernel, you may not be able to do the full thing because it'll be quite expensive to build a full RTOS. So custom build kernels like what we saw, you may build what is needed for you. If I need very simple shared memory is good enough for my inter-task communication, I'll just stay with that. Or if I need messages, I'll build only that. So custom build kernels can be very simple or very complex based on the need of that class of devices that you are building as a company. Okay. So these are RTOSs. Then we move on to Linux. Linux actually has the standard abstraction Linux is called a process. See, the difference between a task and a process is, in a process, the memory that the process uses is protected from other processes. In Linux, if you start one process, its memory space is only visible to itself. Other process cannot accidentally write into this memory. Only way they can do is there is a special mechanism called shared memory. You'll have to explicitly, both the programs have to agree that we will use shared memory. There are some system calls to allocate some shared memory. Once you allocate the shared memory, then the processes can share information using the shared memory. But as long as you're not using it, if I write one code and you are writing one function, we are both running on the Linux system, my program cannot cause any problems to your program because I cannot access your program's memory. I can only access my program's memory. That is typically achieved by what is called as a virtual memory. So virtual memory is standard in Linux systems. So this is supported by the hardware with units like MMU and stuff like that, memory management unit. So each process has its own virtual address space and physical memory, because you will need real memory to run the program. The operating system will allocate real memory as needed for your virtual memory. And virtual memory is all protected. So if I when I access one address, I am actually accessing in my virtual address space. Say for example, I have an address in my program. For example, I say address F2000000, for example, right? So this is in process 1. Process 2 also may have F2000000. But physically, they are mapped to 2 different actual RAM locations. That is the job of the MMU. So because what the programs use, these addresses are called virtual addresses. These are called virtual addresses. That is what the programs internally use. The MMU will translate it. The operating system's job is to allocate physical memory and map this virtual address to physical address. And the operating system will make sure it doesn't map the same physical page to both the process unnecessarily. It will do that only for the shared memory concept. Otherwise, it's all separate. So that way in Linux, it's easier to develop a robust system because if you're dividing your application as all different processes, it's easier to debug because one process cannot accidentally corrupt another process. Whereas if you look at an RTOS typically, Standard R classes, they generally don't provide you protected memory. All the memory is generally shared. So if I wrote some wrong code in one of the tasks, I may be actually corrupting a data which is used by another task actually, because the memory is all shared and common actually, okay? And inside a process, you can have what is called threads, right? Within a process, your whole application can be split into threads. Threads all share the same address space because the threads are all within a process. So the process address space is common to all the threads, okay? So in that sense, threads you can imagine are like the tasks in a real-time operating system. So I can build my whole thing as one application. Inside that, I can split it into threads, but they're all within the same process address space, and they can in turn, communicate with each other or whatever. And Linux again provides good inter-process communication, synchronization, a lot of system support is available. And the best thing about Linux is excellent support for storage and networking, right? So you have all the protocols in the world available, from TCP/IP, anything above that, all kinds of storage devices are supported. So it's easy to build a lot of these things with the Linux platform because very good support is available. Also, if you're building more complex embedded systems which needed embedded real-time databases, or you need some key value stores, there's a whole lot of middleware components also available on Linux, which can be easily used to build your entire application. Or you're trying to do some IoT device, you want to connect to the cloud. So a lot of facilities are available on Linux. Pretty much you can build it in any language support, right? If I'm building a Linux application, I can build it in Python, Java, whatever. There's whole range of languages available to build my application in Linux. So that system, I can build it in Python or Java or C or whatever, right? Whereas in an embedded system, it's difficult to provide because Linux has a lot of memory, so it can support a Python interpreter or a Python runtime or a Java runtime, no issues. Whereas on an embedded device, it's difficult to support all of that actually. So typically, embedded devices mostly are programmed in C, and you download the code and run it. And as I said earlier, also some flavors of Linux support a lot of new scheduling classes like real-time class and all that. So it's easier to build systems which have more stringent time constraints, with using those real-time scheduling classes which are available in the modern flavors of Linux. Maybe originally it was not there, but more and more, as people saw that Linux is getting adopted for many of these embedded devices, more and more support is also coming in. So that's one of the reasons Linux is still getting popular, and it continues to be popular in the embedded world as well, because there is support, protection. So unless your device has very tight constraints in terms of cost, price, memory footprint or whatever, it's many devices, if they can afford to have a bigger processor to support Linux, people go for a Linux-based system actually. So again, ultimately, it depends on finally what you're building. As I said, right, the embedded systems has become a very wide spectrum, from the remote control to a router. It's all embedded systems. So depends on where you're operating and what you're building. What you need to choose and what you need to do may be different actually. So finally, summarizing, right, we kind of looked at a typical architecture. We saw the Renesas processor as an example, and then we looked at a typical all the peripherals in the processor, what each of those peripherals does. We looked at the system segment, ROM, memory segment, peripheral interfaces, analog blocks, all the peripherals which are supported. And then we looked at the different software architectures, which could be from a simple tight loop to a Linux. So whole spectrum is available, and essentially, it all depends finally on what your hardware and software you choose based on your end application. That's why it's very, very specific to what you're trying to build. So the hardware you will choose, the software architecture you will choose, everything is very closely tied to what you really want to do. Okay, so that's really the summary of this session. I think that's probably the last one that we had. So I'll stop here. I think.